Hi guys, today we're on Unit 11, Lesson 1, and we're going to be talking about average and instantaneous rates of change. Basically, calculus is the study of rates of change, and we're going to today discuss the differences between the average rate of change and the instantaneous rate of change. And over the next couple of minutes, next couple of days, we're going to see how this led to the development of calculus. So in calculus, the average rate of change is the slope of the line between 2 points on a curve. We can also refer to this as the slope of a secant line. And we did talk about this earlier in the year. If we have some given function, and I'm just going to do some general kind of function there. If we take 2 points on that curve and draw a line connecting those 2 points, right? So here's my curve f of x. Here's my secant line. The 2 points, the line between the 2 points connecting the curves. We can find the slope using our slope formula. x1, x2, y1, y2. So for each of these points, x1, y1, x2, y2, if we set up our slope formula, y2 minus y1 over x2 minus x1, we get the slope of the line. Therefore, we get the average rate of change. Okay. When we move into higher levels of math, we need to adjust our notation. We did go through this earlier in the year. We said let one value be c and what the other x2 be x. So this becomes c, and my y value can be represented as f of c, x, and f of x. So the slope of our secant line can be y2 f of x minus y1 f of c over x minus c. And sometimes I will also just kind of use a and b. They're all the same thing. All three of these formulas are the same thing. We analyze them the same way. Lastly, I may use AROC as average rate of change. And sometimes I just say slope of a secant line. So, when I'm talking about this stuff, if I'm going to abbreviate it in your notes or on a worksheet, you may see me refer to either the average rate of change as AROC or the slope of the secant line. Okay. So if we take our first example, and we're just kind of taking the average rate of change over each interval. So if f of x equals x squared, I want to find the average rate of change on the interval 1 to 2. Let's, before we begin, talk about what we're actually doing. So f of x equals x squared is the graph of y equals x squared. And I'm going to kind of try to make this a nice big graph for us to work on. So our x squared, our parabola, 0, 0, 1, 1, 2, 4. I'm not sure if that's going to do what we have to do, but hopefully it'll be okay. Okay, so there's my picture, y equals x squared. Basically, if I want to find the average rate of change on the interval 1, 2, I'm looking to find the slope of the secant line. I want to make it noticeable. The slope of the secant line. So really in this interval, this is an A and this is my B, or my X and my C and my X. In either case, f of B minus f of A over B minus A. How do we get f of 2? We plug 2 into our function. How do we get f of 1? We plug 1 into our function. Easy enough to do in our heads. So I have 4 minus 1 over 1. So my slope is 3 over 1, which is 3. So going back over to our picture, basically, we just found the slope between the line 1, 1 and 2, 4, right? Because when I plug in 1, I get 1. When I plug in 2, I get 4. So those are my points. See, this one's hard to draw. The slope of this secant line is 3. Now, let's take, and instead of going from 1 to 2, let's find the slope between 1 and 1.5. So I'm going to be at that point, and 1.5 would be about there on my curve. Let's draw the line first. So this time, we want to find the slope of that line. Well, again, A, B. The slope of this secant line is going to be f of 1.5 minus f of 1 over 1.5 minus 1. So you just have to do a little bit of work here. If we go into our calculator, I can go clear that out. X squared. Let's say I want to plug in 1.5. So my y value is 2.25. 2.25 minus f of 1. No, that's just 1 over 0.5. So we're going to do a little, just math here. .25 divided by 0.5. And you get 2.5 as your answer. So the slope of this line, right, the slope of this secant line is 2.5. Now let's look at the next. Now we're going to go from 1 to 1.25. So now on my graph, I'm going to use this point, and on the x value I'm going to plug is 1.25, so that would be about there on my parabola. So that would be the secant line, and we're looking to find the slope of that line. F of 1.25 minus f of 1 over 1.25 minus 1. And you would, again, plug each value in. I don't care how you do it. I'll go this way this time. We get 1.5625 minus 1 over 0.25. When you do that math, you should get 2.25 for your slope. And now we're going to go between the points 1 and 1.25. So 1 is my new 1.25. That would be the point on that parabola that we can barely see anymore. And we're going to find the slope of this secant line. And I'll give you a second to work that math out, or pause the video for a moment. And you should get 2.125. So all we did is on our given function, we just found the average rate of change between the 2 points on the line. And that's something that you should already know how to do from previous courses and what we did in the beginning of the year. What if we wanted to know the rate of change at one specific value? So let's go back to our x squared curve. Now I don't have to make it so fancy this time. So what if I wanted to find the slope of this time, the slope of the tangent line? Okay. So instead of hitting 2 points, I want to know the slope of this line. Remember, tangent line's a line that hits a curve at one point. So what is the point on this graph? So the point we're going through is 1, 1. What are we looking for? Again, we're looking for the slope of that line. What do we need? Think about it. What do you need to find the slope of a line? We find the slope using our slope formula, which depends on 2 points. What's the matter here? We only have 1 point. But think about it. Let's go back up to our other picture. What is happening to the slopes of our lines as we move our point closer to 1, right? So as we move this value closer and closer and closer, our slopes are getting closer to 2. In math, when we do this kind of process of moving something closer to another value, what is that process called? We're evaluating a limit, correct? So the slope of a tangent line is going to be the limit as x approaches c of the slope of our secant line. And generally speaking, in most textbooks, you will see that notation. So I'm using the f of x minus f of c version. All right. So now we call this slope of a tangent line the instantaneous rate of change. Instead of the average rate of change between 2 points, we want the rate of change at one specific value. So as x gets close to c, we can find the slope of the tangent line by evaluating. I'm going to have you write it one more time. The limit as x approaches c of f of x minus f of c over x minus c. When we use this rule, really easy. Okay, whenever we want to set up a tangent line, we set up our limit first. And then we use our given rule and we use the given x value and then we evaluate. Okay, so let's go back up and finish up. We pretty much already know on our top example here, we want to find this slope again. Think about from the above example. What do you think we should get as an answer? As x approaches c, what's happening to my slopes? They're getting closer to 2. Well, let's use our definition. Let's use our our slope of a tangent line formula and see if that in fact happens. So the slope of the tangent line equals the limit as x approaches 1, right? Because that's the value we're finding the slope of the tangent line for, of f of x minus f of 1 over x minus 1. F of x was really just x squared. What is f of 1? F of 1 is the y value of the point, what you get when you plug x into the function. So x squared minus 1 over x minus 1. When I evaluate that limit, I know I get a 0 in the bottom. So I have to factor, reevaluate the limit. So the limit as x approaches 1 of x plus 1. And my slope is indeed 2. So the instantaneous rate of change, or the slope of the tangent line, at that point is 2, which makes sense from what we did above. So in these next couple of examples, we're just going to real quickly use our formula we just established. We're going to set up each limit, and we're going to find the instantaneous rate of change, or the slope of the tangent line, at each of the specified values. We don't need to make a picture. If you want to, you can to help you, but there's no picture involved. We're just going to set up the limit and evaluate it. F of x equals x squared minus 5x at x equals 2. So the slope of the tangent line is going to be the limit as x approaches 2. F of x is my given function, 2x squared minus 5x. Now I'm going to plug 2 into this function. You can use your calculator for this. 8 minus 10, so I get negative 2 minus negative 2 over x minus 2. After a while, you're going to kind of adjust and just, make that positive in the very beginning. But when you're setting it up, you should take your time. 2x squared minus 5x plus 2 over x minus 2. When I plug in 2, I'm going to get a 0 on the bottom. So I am going to have to factor this. It is a tricky trinomial, so it's going to take me a moment. 2 numbers to multiply to 4 and combine to give me negative 5. 2x minus 4, 2x minus 1. Now, when I reevaluate this limit, when I plug 2 in, I get 3 as my answer. So the slope of the tangent line at x equals 2 is 3. Again, we're looking at a parabola, and it's going to be that slope of where that tangent line hits that curve at that point. F of x equals 3x minus 4 at x equals 1. Slope of the tangent line is going to equal the limit as x approaches 1 of f of x, which is our rule, minus f of 1. Plug 1 in. 3x minus 4 minus negative 1. We're just going to add 1. Three x minus 4 plus 1 is going to be 3x minus 3. When I plug in 1 for x, I get a 0 in the denominator. Go back up, factor, reevaluate this limit, and we get 3 of our as our answer. Think about what's happening here. Okay, why didn't I have an x left? Well, if you think about it, if we look at this function, this is a linear function and the rate is constant. So you're always going to have your average rate of change is going to be your instantaneous rate of change, because in a linear function, the rate of change is constant. And we will kind of go back to that every once in a while, that concept, because that's important. If f of x equals 3x squared minus 4x, and we want the slope of the tangent line or the instantaneous rate of change when x equals -1. Maybe kind of running out of room here. I'm going to set it up over here. The slope of the tangent line equals the limit as x approaches -1 of f of x minus, well, what do I get when I plug in -1? Now, x minus c is x minus -1, so be careful there. When I plug in -1, I know I'm going to get a 0 on the denominator. So I'm going to factor and reevaluate this limit. Two numbers that multiply to -1 combine to give me -4 minus -7 plus 3. So I'm going to take those factors, put them back up in my limit. Reevaluate the limit. And our answer here is -10. So again, that answer is the slope of the tangent line at that point. In our last example, we're going to do 3x squared minus 4x at the point 0, 0. F of x minus f of 0, you can kind of do this one in your head, over x minus 0. Well, basically, this just becomes, actually, I'm not going to rewrite it. When you see x minus 0 on the bottom, that's really just what? X. So I have the limit as x approaches 0 of 3x squared minus 4x over x. I am going to get a 0 in the denominator. X's are going to cancel when I reevaluate. 3 times 0 minus 4 equals -4. And again, think about what we did here. If I just kind of, the graph, y equals 3x squared minus 4x. We look at that graph, okay, we have a parabola. Kind of looks like this, kind of, it's going to be bad. What did we just do? Okay. We just found, on the same picture there, we just found the slope of the tangent line when x equals -1. My slope is -10 for that line. And when x equals 0, we found the slope of that tangent line. And can you see how it goes from like more steep to less steep? It's pretty obvious, okay, what's happening there. And using this process, we could get the slope of the tangent line at any given point on that curve, okay? So tonight, what I want you to do is practice using this formula. It's very important that you just get the process down. Okay, thanks, guys. See you soon.